This is Higher Notes, Unit 1, Section 4, Collisions and Explosions. In Part 1, we will look at momentum and collisions themselves. Well, firstly, momentum needs to be clearly defined. Well, momentum P, small p, is simply defined as the mass of a body times its velocity. So we're imagining some sort of body, mass m, moving along at velocity v. Let's tidy that up slightly. And the momentum of that body is defined simply as its mass times its velocity. And we usually symbolize that as P equals mv. So there's the simple momentum equation. The mass, of course, must be in kilograms. The velocity is in meters per second. And this is therefore the momentum. And that will be in kilograms meters per second. And momentum, of course, is a vector quantity. Direction matters. So as with all vector quantities, you should always indicate the direction of momentum whenever you're specifying it. So for example, if we had a mass of 5 kilograms travelling along at a velocity of 2 meters per second, the momentum above P is simply mv, which is 5 kilograms times 2 meters per second, 10 kilograms meters per second, in this case to the right. So that's momentum for you. Momentum, it turns out, is an extremely useful quantity because there is something called the law of conservation of momentum. Momentum is one of several conservation laws in physics, and this is another law which you should memorize. And don't forget the bit at the beginning. In the absence of external forces, the total momentum before a collision, that's a collision between two bodies, equals the total momentum after the collision. That's something you should commit to memory and employ it whenever you're dealing with momentum problems. Don't forget the bit in red. It's only true if there are no external forces. Nothing from the outside pushing any of the bodies or pulling any of them. So let's do an example then. That's the best way of showing you how this works. Okay, so let's imagine that we have a body like this, which we'll call M1, and we'll make it 5 kilograms. And it's originally moving to the right with an initial velocity u1, which we will make 2 meters per second. And it collides with a stationary body, we'll call it M2, which is a mass of 1 kilogram and is at rest. Okay, so we'll call this our before the collision. Okay. And they're going to collide. M2 is at rest here, but it needn't be at rest. It could be moving, just be aware of that. And then afterwards, let's imagine that our first body, M1, 5 kilogram one, it will be going a little bit more slowly, so we'll call that V1. Let's imagine it reduces its velocity to 1.8 meters per second. The question then is, what must the new velocity, we'll call it V2 be, for M2? Well, we can use the law of conservation of momentum to work this out. So, solution. Always separate out your before and after situation. So we can always begin with the law of conservation of momentum. So the total momentum before the collision is going to always equal the total momentum after. Okay. Now you now need to get that into an equation. So it's M1 U1 plus M2 U2 equals M1 V1 plus M2 V2. Okay, momentum, remember, is mass times velocity. And you can see that everything on the left of the equation relates to before the collision, and everything on the right relates to after. So that's the way to set down your working. Make sure it's before and after. Now, there should only be one unknown, and it's V2. So let's put in the numbers. 5 kilograms at 1.8. So we've got 5 kilograms times 1.8 meters per second. Put that in brackets to keep it tidy. The smaller body, M2, is at rest originally, so it doesn't have any momentum before the collision. Afterwards, the 5 kilogram mass has slowed down a bit to 1. Oh, sorry, I've put in the wrong figure there. Let's just change that. That's coming in at 2. And it's going at 1.8 afterwards. Okay, and we've got our 1 kilogram times V2 there. So just make sure you get the right masses in the right place. So 5 times 2 is 10, so 10 kilograms meters per second is equal to 5 times 1.8. Which is 9 plus V2. So V2 then is 10 take away 9, 1 meter per second. Now it is a vector quantity, so you need to specify direction, and the easiest thing to say is in the original direction of the 5 kilogram mass. And that's a simple conservation of momentum problem. Notice here that the bodies stay separate after the collision, they don't join. It's very important that you check whether they're joined or not. Let's do a second example where the bodies do join. So let's make this our before and this our after. So this could be, for example, 2 cars. Let's make the first one be 800 kilograms, and it's coming in at 20 meters per second. So that will be M1, and it bangs in to a second car, which is originally at rest. Let's imagine that this car has mass 1,000 kilograms, and that afterwards they join together, so they get stuck, sort of like that. Okay. So you've still got your 800 on the left and your 1,000 on the right. And the question is, what speed do they go off at together? What is their joint speed? Well, the solution, as before, is that the total momentum before the collision will always equal the total momentum after. And when we put that into symbols, M1U1 plus M2U2, I'll probably put those in brackets just to be on the safe side there. And notice that on the right, because the two bodies join together, it's essential that you put the two masses in a bracket with a single common velocity v. So you've now got 20 times, 800 times 20 plus 0, because that one's at rest, equals 800 plus 1,000 times v. V should be our only unknown now. So that gives us 16,000 kilograms meters per second, and that equals 1800 V. So V equals 16,000 divided by 1800, giving a common velocity of 8.8 meters to the second per second in the original direction of the 800 kilogram car. There we are. So those are the two types of collision you will meet. One where the bodies bounce off each other, and the second one when they join together. Both very similar, except when they join together, it's essential that you have the brackets around the two masses.